Lacey Spaghetto. I'm an optomechanical engineer at ZMAX, and in this webinar, you're going to learn how to design mirror geometry using the mirror surfaces that load from an OpticStudio design file. So in order to design these mirror components, we are going to learn how to reference the mirror surfaces to create the physical mirror geometry. So when a mirror has been loaded with just a surface, you can copy that geometry, the shape of the mirror, to actually create a mechanical component that represents the optical surface. And then after that, you are going to analyze whether the physical mirror geometry that you've created affects the optical performance, and if it's the same as before when just the mirror surface was present. And then at the end, we are going to review some of the changes that we have made in the way that LensMechanix calculates beam clipping and image contamination. So we've heard some feedback that the way that it was previously being calculated wasn't intuitive for users, and in some cases it wasn't calculating it for the type of system that they were running. So we changed the way that we do that. So we'll go over those calculations and those changes. So we'll start off talking a little bit about OpticStudio's sequential mode. Most optical designs are actually done in sequential mode. This is because it's easier to design, it's faster to optimize the system, and in sequential mode, most components are defined as surfaces. So for example, a standard lens will have two surfaces, the front and the back. So in the image below, the left shows the front surface, and that is surface 2 in the lens data editor. And then in the right image, you can see that surface 3 is the back surface of that component. And so this is in sequential mode, and the distance between the two surfaces is actually the thickness of the component. So when you have those two surfaces and you convert a file to non-sequential mode, the two surfaces then become a component with a physical thickness. So that can be shown in the images on the right. So in the bottom image, you can see that in the non-sequential component editor, you have a standard lens and you no longer have single surfaces, and that is object 7. So if you only have one surface defined in sequential mode and you then convert it, that object will still be left as just a single surface. So that means that you'll have a 0 thickness surface in the non-sequential file. And this is actually how most mirrors are defined. So most mirrors are defined as a standard surface with a mirror material. So this surface is left as one surface, so when you convert it, it actually doesn't have a thickness. So if you've tried loading OpticStudio files that have a single surface as a mirror, or just any single surface that doesn't have a thickness, then you've probably seen a message in the beginning that warns you that you are getting this component, but it's still not a realistic representation of the system. And that is because components must have a thickness. So in order to create realistic components, you have to make sure that these components actually have a thickness. So the thickness is how they are mounted and how they can actually have those mirror properties. And so in LensMechanix, you can create the geometry for these mirrors. And as I mentioned in the beginning, you can actually copy the shape of the surface to create that geometry. So in the images on the left, the one at the top are the surfaces of a telescope after it has been loaded into LensMechanix. 3 of these surfaces actually don't have a thickness. And on the bottom, you can see that there has been some geometry built around these components. So to copy the shape of these surfaces, you can use intersection curve is a native SolidWorks tool. So it simply creates a line sketch where a surface and a plane intersect. So this is really useful when you want to match the shape of the surface that has been loaded in the OpticStudio file. So here on the left, you can see just the surface that comes in, and then I've created a sketch using that intersection curve, and then I converted that into an actual physical object, and we will walk through how you can do this. So after you've created your mechanical geometry, you may want to include these physical mirrors in your computational domain, which means you are taking them into the analysis to see how they will react or how they will behave in the ray trace. And that means that you might want to remove the actual optical surfaces that were loaded in the original file. So this can be really useful for checking that the optical performance is still meeting the requirements. And it can also help you move one step closer to manufacture. So if you are planning on creating drawings for these components, creating the actual mirror geometry is going to help you get an actual part and then make your drawings for that next step. Okay, so let's get started. Alright, so the first step is to load your OpticStudio file. So I am about to load the Hubble, which is the ZMX file. I'm not planning on making any changes to the optical components, so I'll leave that checked. And I will load my file. And here is the message that I mentioned. So it reads that the file contains a surface without a thickness, and it will still function during the ray trace. So it still has all of those optical properties, but it's not a realistic representation of the system. So you may want to consider creating actual geometry for that component. So if I zoom out, I'll see that there are 3 components, and I have this surface here, and this surface, which is a secondary mirror. So let me zoom back. This was a primary mirror, this one is a secondary mirror, and it looks like this one is an annulus. So when you click the components, they do highlight in the optics manager. And if you wanted to view the properties for it, you can, for example, I'll click this one, right click, view the optical properties, and here you can tell that it's an absorber, and you can see all of the settings for it, all of the things that define that component. Okay, so before I begin creating the geometry for these mirrors, I actually want to know which side of these surfaces actually is the mirror. So to do that, I am just going to do a default analysis because I simply want to look at the rays traveling through the system, and I'm not interested in the performance yet. So I'll display my OPS and run all my ray traces. Okay, so there's my filled out OPS table. And I can see that the sources are over here. The light is then traveling and hitting the primary mirror. Then it's reflecting off and hitting the secondary mirror here. And it's then going through this sort of an annulus, this circle, this hole in the primary mirror, and going to the detectors. And it looks like this absorber is simply blocking, absorbing some of the rays so that they aren't interfering with the rays after they've hit the secondary mirror. So I will start with building geometry for my primary mirror. Now I will first go to Assembly, Insert Components, New Part. And I'm going to start on the right plane. And to create my curve, to match that curvature of that surface, I'm going to go into Tools, Sketch Tools, and Intersection Curve. And so now I can click the surface that I want to match. So I'll click this side because that's the one that that's reflect the rays. And I've already clicked my right plane when I first wanted to create the part. So it's going to select that already. So automatically it creates these two sketches that are matching the curvature of this mirror. And so it knows that there is a hole right here, so we don't have to worry about that. And now to finish up the sketch or complete the sketch, I'll just go to a right plane view and I can finish up the sketch. I'll add a center line and I will dimension this. And now I will trim this because I'm going to revolve it around my center line. And it automatically selects the center line as the axis of revolution. And so there I have my component. And so you can see that this surface, the optical surface, is actually overlaying the mechanical component. And now if you wanted to check if that mechanical component, that mirror, actually has the same optical properties as your optical surface, the one that originally came in, you can definitely do that. So what I will do is edit my computational domain. So when you first add components, if you have already created an analysis, and then you add a mechanical component, it's going to be saved in the ignored components. So you actually have to come in here and load it back in there. And here is where you can decide if you want to keep this surface, the actual mirror surface, in the computational domain or not. I'm going to remove it for now, just so I can see how this mirror is behaving. And a thing to note is that in the Optics Manager, I'm actually leaving the mechanical component without any surface properties. And that's what we want, because when they don't have surface properties is when the components act as mirrors. So I'll go into my OPS table, and we are going to only run a LensMechanix output because we want to compare it to the LensMechanix baseline. If you were to run a LensMechanix baseline, so that only calculates these values for the optical components. So since we removed that optical surface, you would get a completely different optical surface. So we're only going to run our full LensMechanix output ray trace. We see that we actually don't get much of a difference in our baseline and our output, so that's good. So another reason why you may want to include this component in the computational domain is if it's a component that could potentially cause some more rays clipped here. For example, these rays aren't a problem here because they are coming to the focal point. But for example, if this were smaller, if the hole were smaller, and you wanted to check that the rays aren't actually interfering with other areas of the mirror, that could be a reason why you want to add that component into the computational domain. So I'm going to build a mirror for the secondary component now. Alright, so to build another component, I'll just do assembly, insert new part. I'll click the right plane. I'll start my sketch with an intersection curve. Now I'm going to show you why it's important to select the right side of the surface. Now I know that a surface is technically only one side, but here I'm going to show you what can happen if you click the wrong one, because it does appear as two. So for example, this mirror is reflecting off of this side right here, but if I click this side, and then I complete a sketch, I'm just going to make something very simple here. I'll trim this. Alright, so I created that part. Now I'll go into the computational domain. I'm going to add this mechanical component, and I will take off that surface. And now I'll go into the OPS table and run a ray trace. Alright, so this ray trace is done, and we see that the performance is completely different. Now, taking a look at it, this mirror doesn't have the same properties that that surface had, and that's because the surface is technically not defined on the other side. So it does cause some complications. So I'm actually just going to delete this component. I'll go over here. Okay. And I'll just make a new part with the other side. So new part, right plane, tools, sketch tools, intersection curve. Select that side. And now I can finish this sketch. And with that, I have to go into the computational domain, and I'll add this part back in there. And you can tell that this part is still kind of hanging around there, but it's no longer in the assembly. But that's okay. So now I made a change to my computational domain with my mirror created with the correct side of that mirror surface. And I'm going to run a ray trace to see how that's going to affect the performance. Okay, so that is done, and this is perfect. This is exactly what we want. So now we can close that and see that our rays are doing exactly what we want them to. So they're going through this hole and making it to the detectors. Okay, so we have one more component that still does not have a thickness. So we can go in here. Again, remember that this was an absorber, and we might want to build some mechanical geometry for it too. So what we can do is the same thing that we have done with the mirror surfaces. So I'll insert a new part. I'll make a new part on the right plane. I'll select this surface because this is the one that is blocking those rays. And then depending on your system, your mechanical housing, that's going to kind of determine the geometry of this component. So say you wanted this component, I don't know, to hold your mirror. Okay, so there is my absorber or my mount. And I'll just click this from that, and I'll revolve it around this. Okay. And so what we can do is the same thing that we did for the mirror. So that would be going into the computational domain, adding this part, and removing this part. And this surface was an optical surface, and if we remember when we viewed the material, it was an absorbed material. So if we want, we can actually make this an optical component to define it as a material that has absorbing properties. And this is going to give you the exact same results that the OPS did prior to this new mechanical optical component. That might be what you want to do, but in the real world, no component or surface property is going to be a perfect absorber. So, additionally, creating a custom optical component takes away your optical performance summary. So, and that's because we start getting into more of the optical design, and we really want to limit the optical design that's here in LensMechanix. All of these tools, the optical design is better done in OpticStudio. So I don't want to do that because I want to keep analyzing my performance. So we're going to exit out of this. What I can do is give this one a different surface property. These all have different absorbing properties, but I'm just going to pick black anodize and apply it to that component. And I will just run my ray trace with that component now in my computation domain, acting as an actual mechanical component. Okay, so our ray trace is done. And it looks like our performance is just how we want it. Okay. So now you can continue building your housing, and the rest of the mechanical components will just depend on how you want to design the system. Right now I am just finishing up mating some of the other mechanical components that I've built for this telescope. Alright, here it is. I've mated my mechanical components. I'm going to add the truss, the shell, and the secondary mount to the computational domain. Okay, so I added them all. I will give these a black paint finish, and I will run my last ray trace. And so after adding all of those parts and running a ray trace, I'm just going to show you the entire system with the mechanical components and the rays going through. Alright, so that is the end of the demo. Now I'm going to go over to our slides. So we talked about mirrors and how we can use the geometry of the surfaces to create components. And so I'll take a minute to talk about a tool or a request for a feature that we've received many times. So we have created a fold mirror tool. So the reason why a lot of people would find benefits from this is because many times there can be space restrictions that are mechanical restrictions. So the mechanical engineer needs to rearrange some of the components without having an effect on the optical performance. So this fold mirror is currently being tested. We do have it in an internal version, and so we are testing it. And so, like I mentioned, it'll enable the users to bend any path along with any mated components. So by looking at the images on the right here, you can select the two reference components. So that lets you define where you're going to place your fold mirror. And then you select your target component, which is the last component. Now that should be a detector, unless you're adding another fold mirror after this fold mirror. And then after you add it, it'll bend the beam path, and it'll include any of the mechanical components that have been also mated to those components in the beam path. So this feature will be out in a future release, and it is something that we are excited about because we've gotten lots of requests for it. Now the last thing that I will talk about are the calculations in the Optical Performance Summary. So we have measured the change in spot size, the percentage of beam clipping, and the amount of image contamination. Now these definitions for these measurements are in our OPS table, but we are changing the way that we calculate beam clipping and image contamination. And the reason for this is because we really wanted it to be more intuitive to mechanical engineers and our users. So I'll go into both of those measurements and how we're going to be changing them. So we'll start with the changes in the beam clipping. Before version 3.2, we defined the amount of beam clipping as the percentage of critical rays that hit any mechanical components and did not hit the detector color. So this is pretty much any rays that are hitting a mechanical component bouncing off away from the image plane. And so critical rays can be more complex, and it's more of it might be more of an optics term. So to ensure that more of our users understand what this measurement means, we are changing it. And additionally, the value was commonly misinterpreted. So many users thought that it was actually the total percentage of rays, when it's actually just a fraction. So it's going to just be a more direct measurement. So in version 3.2 and future versions, we are defining the beam clipping as the percentage of total rays that follow an unintended path. And so any rays or paths that aren't like the ones in the OpticStudio baseline, those aren't being counted if they don't follow those intended paths. So this doesn't include image contamination rays. So that would be rays that hit a detector. And so now that we are using the total number of rays, then this is more intuitive than actually using the critical rays. Before version 3.2, we defined it as a percentage of critical rays that hit any mechanical components and did not hit a detector rectangle and hit the detector color. So this didn't work for files that did not have a detector color. So some of the feedback we got was that in files that don't have a detector color, so mostly files that come in as non-sequential, they were getting an NaN in the OPS table, and that isn't very useful. So we did include it, we did make this change so that we could have an image contamination value for those type of files. And now in version 3.2, we're defining it as a percentage of total rays that follow the unintended paths and hit any original detector. So a few notes on that. This is the rays coming from all sources. So if you add a custom source, that's going to be also included. But if you add a custom detector, those aren't going to be accounted for in your image contamination calculations. Those are two important distinctions there. And so now that, with those changes, you can actually calculate it with any detector type. And so on the bottom, just a little image with the navy blue rays are the ones on pointing to on the left. So this is image contamination. You can see that they are hitting the mechanical component close to the front, which would be the right of the picture. And then they hit the detector color, but not the detector rectangles, which is where those rays come to the focal point. And on the right, you see the beam clipping rays, which are a little teal color. So those are just hitting the mechanical component and going away. So they're not actually going to the image plane. And to summarize our key takeaways, we talked about how most optical designs are actually beginning in sequential mode, and then they're later converted to non-sequential mode. Sequential mode is ideal inputs. It's easier to design in sequential mode, and it's also easier and faster to optimize. Non-sequential mode is converting the ideal inputs to manufacturing inputs. And so when we are in LensMechanix, we do work in non-sequential for that reason, because it's more realistic. So when you are getting a file that has a surface without a thickness, you can actually use it to create a mirror geometry in LensMechanix. So there is no need to send it back to your optical engineer. You can easily analyze the performance of the system with those mirror components instead of the surfaces in the computational domain. The fold mirror tool is in testing, so that will be in a future release. And beam clipping and image contamination calculations are going to be more intuitive, so you can better understand any issues in your optomechanical assemblies. Now, if you have any feedback or any of these tools or feature requests, please let us know. We really appreciate that feedback. And you can submit any questions in the questions box. You can go to www.zmax.com/lensmechanics to download a free 2-week trial. And for your feature requests or any other questions, please contact sales@zmax.com. Okay, so the first question is, does LensMechanix also function in sequential mode? So the answer is no. LensMechanix only does non-sequential ray tracing. And so I kind of mentioned that at the end. The reason for that is because ray traces in non-sequential mode are more accurate and get you closer to a design that is ready for manufacturing. So we want to take the design process forward, and going back to sequential mode can be useful for making certain changes to the optical design, but it is taking a step back. So that is why LensMechanix only functions in non-sequential mode. And additionally, you can load both non-sequential or sequential files into LensMechanix. And your files that are in sequential mode will be converted to non-sequential. So we use the same converting tool that OpticStudio does. Is the fold mirror tool limited to just one fold mirror per assembly? So we don't limit the number of fold mirrors that can be added. We are still testing that, so there's still a little bit of work to be done there, but we won't limit the number of fold mirrors. One limitation of that tool is we do want to keep the beam path the same as the original optical design file, so that will remain the same. So with that, you might find some limitations when you start adding 2 or 3 fold mirrors, but overall there isn't a complete limitation. About the fold mirror is a fold mirror added as an optical component or a mechanical component? So the fold mirror will be added as an optical component. And the follow-up question is, can you add fold mirrors that are curved? So as of now, you won't be able to. So the fold mirror is added as an optical component that is flat. And right now, or in the first version, you will have the option of adding it as a circle or as a rectangle. That is just a flat surface. And that is because it is an optical component, so we want the optical engineer to be able to re-optimize if they need to. So that means that when the mechanical engineer, or if the mechanical engineer adds a fold mirror, then that file can be sent back to OpticStudio. So that means that the optical engineer can then re-optimize that system and the actual fold mirror. And if the optical engineer wants to change it to a curved surface, then they can do that in OpticStudio. Are the changes to beam clipping and image contamination already available in the current version? Not as of now. We are testing that. Does LensMechanix do ghost ray tracing? Are rays split in LensMechanix and then propagated forwards or backwards in the system? Yes. So when you are running or going through your analysis settings, you have the option of enabling ray splitting. And so in this demo, I just did a default analysis, so I skipped all of the settings. But if you go to analysis, start analysis, analysis wizard, the analysis wizard will step you through all of the steps to set up that ray trace. And there you have the option of doing analyzing for simple image quality and light scattering, or enabling ray splitting as well. So with ray splitting, you will be able to analyze for ghost images, and also you'll see those rays the rays reflect and refract through the system. Can a new field point or rays be added in LensMechanix directly to be traced? Yes, so you can add custom optical components in LensMechanix, and you can add sources, lenses, and detectors in LensMechanix. And so you will just then need to run a new ray trace, and then you'll see the results of that. We always recommend that if you do add certain sources and they're actually part of the optical design, that they are sent back to OpticStudio. But if you wanted to see, for example, if you wanted to try to simulate the sun and just see what happens when there's extra sources to the side and see how that affects the optical performance, you can do that. Why wouldn't the mirrors be designed in OpticStudio? That is a good question. So the mirrors can be designed in OpticStudio. However, there are a few reasons why they might be designed in LensMechanix. So one reason is that sometimes the optical engineers will just design and optimize that surface that has the optical properties, and that is great. That's what we need, and it is very common for the mechanical engineer to actually have to design the mounts. So that is why you might want to design the mirrors in LensMechanix. You can do it in OpticStudio, but again, it's just the surface. Although there are ways to define a fold mirror with a thickness, but most of the time it is done with a surface. And additionally, adding a fold mirror, it is sometimes something that the mechanical engineer has to do, and that is because it could be because there are certain space restrictions. So many times the mechanical engineer is given those space restrictions. So they have to bend the beam path within a certain, to keep it within a certain area, and that just means that they have to add the fold mirrors themselves. So that is why we have gotten that request so much, and it is something that lots of mechanical engineers value. When a LensMechanix file is sent back to OpticStudio, is it converted to sequential mode? No, so that file stays in non-sequential mode. Don't believe that OpticStudio has a way to convert non-sequential to sequential files. So if we do mirror lots of the functionality that OpticStudio does. So again, that would be sort of like taking a step back to the original design. So the file will stay in non-sequential mode. And to add to that, the non-sequential file, or the output file, will also include any mechanical components or any changes that haven't been made to the original design. Is there a free demo version of LensMechanix? Yes, so it is on our website. It's 2 weeks, and you can find it at just www.zmex.com/lensmechanics. And you'll just need to fill out a form with your information, and then we'll send you an activation code. So we do encourage you to try it out. All you need is to have SolidWorks on your computer, SolidWorks 2015 or later, and you don't need OpticStudio to run it on your machine. I'll wait a few minutes in case there are any other last-minute questions. Does LensMechanix load multiple configuration files? Yes, we do. So this is something that we recently added, and we currently load the non-sequential multi-configuration files because sequential, if you have a sequential multi-configuration file and you convert it to non-sequential, only one configuration is saved. So again, that's just a limitation of both OpticStudio and LensMechanix. However, in the future, we would like to support that conversion so that if you have a sequential multi-configuration file, it will also be supported in LensMechanix in non-sequential mode. If you have any questions when you download the trial, please email us at sales@zmex.com and we will answer all of your questions. Thank you for attending.